Okay, I'd like to start today um, talking about the last homework, which is homework 7. So this is a relatively short homework, just 3 problems. But one of these 3 problems, 14.1, involves the use of a model checker. You'll have to run some software. And this software has been installed on Cori.ecs. So all of you should have access to it. So you just log in, and I think there are both Linux and Solaris binaries, so you can run either one of those. So what I want to do is give you a quick demo of how to use Spin. It's really easy. In fact, we've made it such that you don't really have to write too much of the part of the model. It shouldn't take you more than half an hour, okay, to do it, assuming the installation works for everybody. So what I encourage you all to do is, although we have tested out installation for the GSIs, if you can log in and check if you can run Spin, and let me know quickly if you have any problems. Okay, so let me tell you what the problem is. So the problem 14.1 is about an example we've seen earlier in the course. This is the interrupt-driven program where you had a main function which has a loop which checks the value of timer count, right? Timer count starts at 2000 and it gets decremented once every time the ISR is called. Okay, so that's the model that we're going to deal with, and the property that that you have to check is the same property that we talked about earlier, which is assuming the interrupt occurs infinitely often, is state C always reached. Okay, so you already have this state machine model. So what I'm going to show you is an encoding in the language, in the input language of the Spin model checker of essentially this model. But it's not quite right. So your task is to fix the small portion of the model which is not right. Okay, but I will go through the syntax. And so everything you need to know about the Spin programming language, all the syntactic constructs are already there in the model that I'm going to show you now. Okay, so just to remember, just to recall this model, you have this is the system model. So you have 2 top-level modes, inactive and active. Inactive is when the ISR is inactive, and active is when the ISR is running. And in the inactive mode, the main function runs, and it has 3 states it can be in, 3 program locations, A, B, and C. And then the ISR has 2 locations, D and E, right? So, so let's look at the Spin model for this. So I'll first go through the Spin model, and then I'll show you how to run it. Okay, so it's sort of based on a typical imperative language, but it has some weird programming constructs and conventions. So let's just go through it. So the basic idea is that you define each state machine as a process. Okay, so the state machine that I just showed you is defined as the sys process. That's the system. Okay, so proc type is just the type, it's a process type, and active means when you start running the model, this process is active. Okay, it's in the initial state. Okay, so that's the system process. Then you have another process which is the environment process. Okay, so if we go back and look at this picture here, we have this input assert, right? So assert is an input to the system model, which is generated by the environment, right? There's an external interrupt. So for Spin, you have to model the environment also. So we've done that very simply here. So the environment just has an infinite while loop, which is written like this: do and OD, right? That's the while loop. And inside the while loop, all it does is it executes this statement. Now, what is the statement doing? The statement is writing an assert to a channel. Okay, so the way Spin works is the model you can have in your mind is there's the environment and then the system, and these are actors, and the environment has an output port, which think of it as a communication channel. That's how Spin models it. And this communication channel has some associated buffer, Okay? And likewise, from the system to the environment, you could have a return channel. In this case, we don't have a return channel because the environment doesn't have any inputs. Okay? So the environment has one channel going from its output to the input of the system, and this channel is called assert chan. Right? This is what I have here. That's the assert channel. So so we declare these channels up here. So here the declaration says I have one communication channel which is called assert chan. Its associated buffer has size 1, and the type of message in the channel is M type. And M type is either assert or return. Okay? So in this case, if you go back to this example, there are the input signal can either be assert or return, right? So basically, there's two kinds of messages we have to deal with, either an assert message or a return message. Okay. Now for this channel, you only ever write asserts. There's no return here associated with this channel. Now inside the system, though, there is a return input and output port. Okay, so if we go back to the model here, you'll see that return is both an input and output, right? It's generated by the ISR state machine. It's an output of the ISR state machine, and it's an input to the top level model. Okay, so for that reason, we have another channel called return chan, which also has the same buffer size and same type. So the buffer size is just saying how many messages can be on this channel. And in this case, we are modeling something which effectively is just a wire. And so the buffer size is just 1. Okay? So there's two channels in this program, the assert channel, return channel, both of the same type. Everybody with me so far? Okay? Now there's a shared integer called timer count. So we've declared it up here in timer count initialized to 2000. And then we have a few variables that correspond to the internal states of the state machines in the system. So mode is a variable which corresponds to the top level mode, either inactive or active. Okay, and so it's declared within spin to be a byte-sized integer, and it has value either 1 or 2. The value 1 corresponds to the initial mode, which is inactive, and the value 2 is the second mode, which is active. And then you have these two variables which correspond to the state of the machine. So this state machine has 3 possible states, and this state machine has 2 states. So the state of the main function is in this variable, main state. And the state of the ISR is in this variable, ISR state. Okay? That's it. So it's just modeling the hierarchical state machine that we had on that slide. So now let's look at the actual model of that hierarchical state machine. So it's also going to be, it's a process which has an outermost while loop, an infinite while loop, which makes sense because the state machine runs forever, right? You start it off and it keeps looping between the states. One thing to note is where, even though here C is like a dead-end state, we have an implicit self loop here, okay? So once the system gets to C, it just loops in C. So, all right, so let's look at what's in here. You have inside the while loop, you have an if statement, right? So the if statement goes all the way down. So the syntax, again, is similar to the do or the while loops syntax. You have an if, and then it terminated with an fi. And inside the if statement, you have 2 conditionals. So every conditional has a starting double colon. So a double colon means here's a new branch of my if statement. And this is actually, although it's called an if statement, it's really more like a switch. So you can have multiple conditionals. So in this case, there's 2 possibilities. Either mode is equal to 1, which is the inactive mode, or mode is equal to 2, which is the active mode. Okay? Now let's look at inside the inactive mode. If mode is equal to 1, then you have the main function, which itself is a state machine. So you have another if statement. Okay? Now let's ignore this part for now and look at this one. So it's another if statement which has 1, 2, 3, 4 conditionals, right? And these correspond to the 4 possible edges. So if I go back to the state machine here, I have 1, 2, 3, and then an implicit self loop. So you have 4 possible edges. And so in the spin model, so this edge is saying if main state is equal to 1, which is I'm in state A, and timer count is not equal to 0, then, so you have this arrow which indicates what the action is, then I'm going to set main state equal to 2, which means I'll go to B, right? And this says if main state is equal to 1, which means I'm in A, and timer count is 0, then I'll quit the loop in the main function and go to C, okay? And this one corresponds to if main state is 2, which means you're in B, then go to A, which you'll see there's a loop from B back to A, which is unconditional here. Okay? And then finally, the default case is you've reached C, and you just have a self loop, and the self loop is modeled by this skip statement, which is a no op basically, right? So you just stay in the state C and you do nothing. All right? So that models the inside of the state machine, but we also have to model this transition, right? The preemptive transition that goes from the inactive mode to the active mode. The way we do that is by reading the assert channel. So that's the first case here. So this is the name of the channel, and the question mark corresponds to a read operation. Okay? So if you read an assert from the assert channel, then you move from the inactive mode to the active mode. And the way you do that is you execute 2 things atomically. So you set the mode to be 2, which is active, right? Remember, mode equal to 1 means inactive, so mode equals 2 means active. And we set ISR state to be 1. Okay? The reason we do that is because you have a special kind of transition here which always enters the initial state of the active mode, right? So you will always end up in state D when you enter the active mode. Okay, so you set mode equal to 2 and ISR state equals 1, and these two happen atomically, so they happen in the same step of the state machine. So now, if you ever executed this statement in the next step of the state machine, mode will be equal to 2, and so you'll come down here, right? And this is the part you need to implement. Okay, so we'll just go through what we have here, which is wrong, and you have to fix it. So if mode is equal to 2, then there's 2 possibilities. So if you're in the inactive mode, either you execute a transition inside the ISR state machine, or you execute this transition back from the active mode to the inactive mode. And this happens when you get a return. Okay? So here, if on the return channel you read, so you have a question mark again, if you read a return value, then you go back to the inactive mode. You set mode equals 1. Otherwise, you execute the ISR state machine. Now, what I have here is a wrong ISR state machine. So what it does is it starts in state D, which is ISR state equals 1. And it unconditionally, if you're in state D, it goes to E. And here, if you're in state E, it goes back to D. So basically, the state machine that we have here is just this. Right? From D you go to E, and from E you go back to D. And that's obviously not the machine you have there. Right? So here you have a guard, timer count not equal to 0, and here you have an associated action plus an output. Right? So this output will correspond to writing a value on the return channel. And this action corresponds to decrementing timer count. Okay? So we don't have that here. Now, but the way in which you write to the return channel is going to be exactly the way that the environment writes an assert to the assert channel. So the way you write is you just have an exclamation mark, a bang instead of a question mark. Okay? So you have the channel name and then bang and then the type of message. Okay? So somewhere in here in the ISR state, you're going to have to put return chan bang return type. Okay? Questions about this? Right. So we have gone through the entire model. All the syntactic constructs that you need to write this are already in this file. Okay. So I think it should be relatively easy for you to do this. But if you run into any problems, as always, just send me email or send the GSI's email, and we'll figure out what the problem is if you find one. Okay. So let me show you how to run this. So like I said, the goal is you have written down the state machine now, and you want to check a temporal logic formula of the state machine. So I have a Cygwin installation which is not perfect, so I have to do some command line work. But I think you should be able to use this graphical user interface. So let me just show you how you start that. Okay, so so what you do is there'll be a tickle script xpin with some version number. The version number might differ because I have a slightly older version. So xpin.tickle, and then you give the file name, and this file will be provided to you. This is the one that I just showed you. And we'll start it. Okay, it opens up that window. And let me change the font so you can see it. Okay, so that's the same model that we had before. So now the first thing to do is, after you've written up the model, run the syntax checker. Okay, and it says no syntax errors. Okay, so good. So far, so good. Now, you can actually simulate this model. So you can just run random simulations if you want. So you can provide a random seed here, and then start a simulation. And the way the simulation works is on this picture, it shows you a pictorial representation of the two processes running and messages going between them. And this is the main window, and you can single step it. And as you single step it, think of it as like a debugger. It says which process is running. So in this case, it's running the sys process, line 37, okay, and it's received an assert type. Okay, so it corresponds to that receive. Okay, so anyway, so it runs it, and then on the right-hand side, you'll see the window growing where messages go back and forth. It only shows message sends and receives, so there are lots of internal actions that it won't update in this picture. Okay, so that's the simulation. But of course, we don't want to just do simulation, we want to do verification. And so we'll set verification parameters here. So the thing to do is you want to verify an LTL property. And I'll provide you a template. So let me go back and redo it. So it'll open up this window. You can actually write an LTL formula in this window using the standard operators. So here they use box for globally and diamond for eventually. This is until and so forth. But I'll just give you a template, and you should be able to modify the template. Okay, so the template is demo.ltl. Okay, so it's basically, this is a different property from the one you'll write. So it says eventually you reach program location B. Okay, so in B is defined to be here main state equals 2. Right? So the state of the main function is B. And then the rest of it you can ignore. This is automatically generated by Spin. So if, generate would just generate an automaton that Spin uses internally to represent the property. And then we run verification. Okay. Now I'll write this down in the instructions associated with the assignment. You have to check that box, weak fairness, run it. And as you can see, it doesn't work on my Cygwin installation, right? So it ran one command, but it couldn't run GCC. So I'll go back and I'll run GCC, okay, with the same options. And then I have to run another command, which is which actually runs the model checker. Okay, that's it. So the model checker ran. Now it generated a counterexample. Actually, let me go back. So it says one error, right? It searched the state space up to a depth of 19. So it's doing depth first search, and it visited various states, and it found an error, and it stores the error in this file called pan_in.trail. Okay, so we have to go back and look at that. So the way you look at that is you go and you run a simulation. So in this case, you run a guided simulation, which means it will just follow the sequence of inputs that's written in that file, pan.trail. Right? So the model checker found a path, which is a path along which you never reach location B in the program. So it's written this path down in this file. So we load that file and then run it, and that's it. So it has it shows this thing where the process environment is running, system is running, and there's a loop. And in this is an infinite loop in which you never visit state B. So what happened here? You can go back and look at the start of the cycle. So it says it was in mode 2, which is the active mode, and then it was initially in state D. From D, it went to E, and from E, it went back to D, and it kept looping. Right? So what happened was, in this picture, it went from inactive to active, and then it kept looping between D and E infinitely. And in the main function, you just stayed in A. Okay? So that's the problem. Now, of course, we know this can't happen infinitely because you keep decrementing timer count, right? But anyway, that's what the counterexample is. Okay? So you have to fix the model to get rid of that counterexample. Now, what the question actually asks you to do is to check that you can eventually reach C, right? And so you have to slightly modify the property to do that. But I'll provide you a template for that property as well. Okay? So the only thing you really need to do is learn how to run spin, like we just went through, and fix this part of the model. Run spin, see if it satisfies the formula eventually C, and if it does satisfy, then explain why, right? But if it doesn't, then you get an error trace, and you have to explain that error trace. Okay? Any questions on this? Yes? Yeah. So this is something we didn't cover in class, but it's the last section of chapter 14, which is how do you check the liveness properties. So the algorithm that it uses is what is called a nested DFS algorithm, which is described in the book. Okay? All right, so do at least try to run spin. So I will upload these files by today on bspace under the same assignment. So you'll have access to all these files. So once I've done that, run spin, and let me know if you have any problems with just running it.
Are you going to post like the commands that you use to run GCC?
Yeah, I'll post the commands also. So in case you have the same problem with the GUI, you should be able to just run 3 commands on the command line prompt, and that'll do it. Okay? So let's talk about today's lecture topic, which is networking. Okay? So again, this is not on the second midterm, but it's increasingly an important topic in embedded systems because all embedded systems pretty much today are networked, right? And we'll talk about networks which are slightly different from conventional networks. So these topics are probably not those that are covered in 122, for example. And in particular, for embedded systems, you really care about real-time behavior. And so on the internet, although it's changing a little bit, timing doesn't matter, right? How long a message takes to get from one node to another doesn't really matter so much. It's not specified as part of the protocol, importantly. Although with video distribution and so forth, we now start caring about timing as well, even in conventional networks. But for embedded systems, it matters a great deal. Okay, and so we're going to talk about some networking standards that are out there today that deal with real-time networking. So in cars, there are 2 standards that are being followed. Control Area Network, or CAN, is one of them. FlexRay is supposed to be the next generation to CAN. And then IEEE 1588 is real-time Ethernet, which is a time synchronization protocol to make sure that if you have a distributed embedded systems, the clocks of the different nodes in the embedded system are synchronized to very high precision. Okay, so we'll talk about all of these. Necessarily, it's going to be a somewhat high-level lecture. I'm going to try to pick a few topics here and there where we can go a little deep, but we won't be able to cover all the details of these protocols. But there's lots of papers and other links that I provided in the slides, so you can read that if you're more interested. Okay, so we'll talk first about CAN and FlexRay, which are the networks that are used in today's cars. So I think I might have talked about this earlier, but today's cars are increasingly moving to doing everything electronically. So that's called X-by-wire. It's amazing. There's software to do a whole bunch of things, including window control. And you would think a window control is just it's a simple mechanical thing, but there's code to deal with what happens if the child lock is on, and things like that. So there's a bunch of different functions, even for something as simple as just window control. Now, what are the things that are on the network in the car? So there's clearly different pieces of software controlling different parts of your car. There's also sensor units and actuator units, and they're all sitting on a bus, okay, and communicating on that bus. So CAN is a way of specifying the protocol that governs how they talk on that bus. Okay, and so the trend seems to be going more and more towards automation, right? And DARPA's Urban Challenge is sort of one extreme point where you don't have the human at all and you have autonomous cars. So here's a few statistics that are quite interesting. So the number of electronic control units. So each electronic control unit is doing one function in the car. So we'll look at the structure of an ECU soon. But the number of ECUs, you should think of an ECU as having at least one microprocessor, right? So the number of ECUs in today's high-end cars easily reaches 100. So you have 100 microcontrollers sitting in your car if you have a high-end car. And the total number of lines of code is of the order of 100 million lines of code, right? So, and it seems to be increasing even more. So a lot of that increasingly is in networking. There's networking inside the car, plus increasingly there's wireless networking as well, right? And an interesting point was that in the current S-Class Mercedes-Benz, just the radio and navigation system contains 20 million lines of code, right? And the total number of electronic control units was almost as much as the A380, which is the state-of-the-art giant plane, right? Long-haul plane. So really the amount of electronics and software in cars is growing very rapidly. And they're all networked, right? So today's lecture is about how does this network really operate? And how can we make sure that it operates in a timely and reliable fashion? So by the way, there's this, if you're interested in this topic, there's a very nice accessible article in IEEE Spectrum that appeared 2 years ago. Okay, so the first protocol we talk about is called Controller Area Network. So it's a protocol that governs how different control units connected on a bus can talk to each other, and it has support for a whole bunch of things. So first of all, this is it's a broadcast medium, and therefore, if you have many different processors that are all trying to talk on the same bus, you need to have some kind of arbitration between them, right? So if two processors want to send messages at the same time, well, who gets to go first, right? The way this is done in CAN is using priorities. So we're going to look a little bit in detail about how priority-based arbitration works. Another question is, well, how do people guarantee timing constraints in something like this? So think, for example, that you have a sensor unit that's capturing the brakes that the driver has pressed, and that sensor unit sends a message on the bus. That message has to be picked up by the control unit that deals with braking as well as other functions. And the latency of that should be bounded, obviously, because if the driver depresses the brakes, then you want that to happen in a certain amount of time. So the overall timing is it includes the timing of the software, which we talked about earlier last week, right? Plus the timing it takes for messages to get through from one node to another. Okay, so we need to be able to do timing analysis for message transmission and compute the analog of worst case execution time, which is called worst case response time. So worst case execution time is for code, right, to determine how long a code will take to run. And worst case response time in the context of CAN is the maximum time from when a node wants to send a message to when the message is delivered. Okay? So we'll look a little bit into ways in which you can do timing analysis. There's lots of other details in CAN which we'll skip over today, like error detection and handling. So here's the structure of a CAN-based system. Each of these boxes is an electronic control unit. And if you look inside the box, at the lowest level, there's the hardware, which contains the processor as well as the CAN interface. And so typically this contains some control. So if you look at the CAN chip, it has a controller, and it has a transmission buffer and a receive buffer. Right? So you have finite buffers. And then you have your actual software, which we'll call the application software. So this is doing some dedicated task. And then that software is running on top of some systems software, which could contain some libraries, plus a real-time operating system, maybe device drivers as well. Okay, so that's the typical structure of a CAN box. And all of these guys are connected on the same bus. So the question is, now let's assume that this task which is running wants to send a message. It wants to put a message on the bus, right? So what is the structure of that message, and what's the protocol that it follows to put the message on the bus? So here's the structure of a data frame corresponding to a message. Okay, so here's when so first of all, the processor checks, the ECU, I should say, checks if the bus is idle. So there's a signal which tells it if the bus is idle. If the bus is idle, it means nobody else is trying to transmit. So this processor can try to transmit. But remember, there has to be arbitration. And the way arbitration is done is that if you have multiple nodes that want to transmit at the same time, they try to write their priorities onto the bus. And there is a mechanism where the priorities get resolved, and people back off if they have lower priority than the other message. Okay? Now, in order to write the priorities in a synchronized fashion, they have to first do some synchronization. And so there's a little bit of time where after the bus is idle, they try to synchronize. And then this part of the message deals with arbitration. So every ECU writes its priority onto the bus. Okay? So we'll see that in a bit more detail in the next slide. And then it does other things. So it writes the message type, it sends the data, it has some error checking stuff. Okay? So we won't spend much time on talking about the details of the data frame, because that's somewhat boring. Let's talk about the arbitration algorithm. So in the arbitration scheme, basically the key thing to remember is that the bus behaves as a wired AND. Okay? And all nodes are first initially synchronized on the start of frame bit. Okay? So let's take an example. Here you have 3 ECUs, and this is the priority. So ECU number 1 is sending a message with priority hex 15A. Okay? So the priority field is 12 bits. So this is the priority of the message sent by the first node. This is the priority of the second node. This is the priority of the third node. Okay? Now these are the binary representations of these hex numbers. Okay? So you have the 3 binary representations of priority. So the way the protocol works is, initially the bus is idle, so voltage level high, and then they all synchronize on start of frame. They try to pull it low, okay, and they synchronize on that. And then they start transmitting 1 bit at a time. So the first bit, so node number 1 will put a 0, node number 2 will put a 0, node 3 will put a 0. They all agree on that. Okay. So the voltage level on the bus is a 0. Then they'll all put the next bit, which is 0 and 0 for node 1 and 3, and it's a 1 for node 2. So remember, the bus behaves as a wired AND. So it will try to pull this 1 to a 0, correct? And so node 2 will realize that it tried to put a 1, but the voltage value after a certain amount of time is 0. So it knows that, that it has to back off. It has lower priority than the other messages, than the other ECUs, right? So node 2 backs off, and then nodes 1 and 3 continue. So they put 1s onto the bus. That's fine, they agree. And then node 1 puts a 0, and node 3 puts a 1. So node 3 backs off. Okay? Now at this point, node 2 has backed off, node 3 has backed off. Can node 1 stop and start transmitting its data? It doesn't know that they're backed off effectively, right? Because node 1 doesn't know how many nodes are on the bus, right? I mean, the CAN bus is supposed to be a configurable bus where you can add ECUs. And so at this point, node 1 doesn't really know that nodes 2 and 3 have, or other nodes have backed off yet. So it will continue putting the remaining bits on the bus.
Is this happening on some specific control line, or is this random data line?
I'm sorry?
Is this happening on some specific control line, or is this random data line?
It's on the real line. Okay. So anyway, so node 1 will keep going. And once it's sent the entire priority bits, if it has not had to back off, then it knows that it has the highest priority, and it will continue with the message. Okay? So one key point here is that all 3 of these ECUs, you have to write to the bus, and they have to wait until they receive values from each other, right? So a sender has to wait longer than the maximum propagation latency on the bus before sending the next bit. Okay? And the reason is, otherwise, if the sender doesn't wait long enough, it's going to maybe wrongly infer that it has high priority, right? When it should have actually backed off. Okay? So, yep. Yeah.
So basically,
Yeah.
right? So then, in that sense,
Yeah. So I mean, so there probably is. This is something I don't know the details of, but there probably is some additional circuitry that will. It's not just the single node that's trying to pull it to a 0, but if that node tries to pull the bus to a 0, then there probably is additional circuit that will try to maintain a 0 level even when you have multiple nodes on the bus. But clearly you have a bound because due to those constraints on the number of nodes you can add, right? So even in theory, if you could have arbitrary number of nodes on the bus, in practice you can't.
They're all open connector outputs, so any node can, they're essentially floating in the
So you have a, I didn't understand. It's a comment?
So yeah,
Okay.
so he was for his question. So
Yeah.
you asking if there are not two nodes, what happens if one guy somebody wants to put it down, any one node.
I see. Okay. Okay. All right. All right. So so this priority-based arbitration imposes a latency already, right? So we want messages to be sent quickly, but you already have a constraint on a minimum bound on how long it takes to send a message, which is imposed by the arbitration scheme itself, right? So for a single bit, you need to wait for twice the propagation delay, the end-to-end propagation delay on the bus, okay? And then this is multiplied by the number of priority bits you have. Okay, so you have a minimum delay already for sending a message on the bus. So the longer the bus, the lower your bit rate, okay, because of this delay. Okay, so so now let's say the goal is really to compute the bound on how long it takes to send a message, right? there's a bunch of assumptions that are made in doing timing analysis, not all of which hold. Okay, so the first assumption that people make are that the clocks of the different processors, so each processor has its own clock, those clocks will evolve at the same rate. Okay, so if this processor measures one time unit, and this processor also tries to measure one time unit, the durations they'll measure will be the same. Okay, but there could be clock skew. So the clock of this processor may not exactly start at the same value as this processor is not the same processor. So the clocks don't have to be synchronized, but they have to evolve at the same rate. The second assumption is that the implementations are correct in the sense that the messages are always transmitted by nodes based on their priority. And so that can be a little tricky because you have several layers. So you don't just have the buffer at the bottom in the CAN interface chip, but you might also have a buffer in the application software and a buffer of messages in the OS layer, right? And so all of those pieces of software and hardware have to maintain the right priority scheme. Okay, and sometimes there could even be bugs that don't represent the right priority scheme. The third assumption that's made is that messages are periodic. So every node sends messages with a certain period, every so often. But there's no assumption made on the relative phases. So ECU1 might be sending a message every millisecond. ECU2 might be sending it every 2 milliseconds, but they don't have to start at the same time. Okay? There's no assumption made about when the message transmissions start. Okay, so let's look at the ideal way in which the scheme will work, right? So you have 3 ECUs on the bus, and let's say each of them has a queue like this. So ECU1 has 3 messages, and you can see that the priority of this message is going to be higher than that one because this has more leading 0 bits than this, right? And this has, so the priorities of these two. So this message has higher priority than this one because you have 2 leading 1s in the beginning here and you have a 1, 0 there, right? So anyway, they're ordered in priority order. And likewise here also. So the lower message has higher priority in each case. And so what you'd expect is that if the x-axis is time, right? So time moves along this axis. So to the right, you have the messages that go the earliest, and to the left, you have the messages that go the latest, right? Then you'd expect that now you have these 3 messages, 103, 122, and 111. Let's say they all arrive at the same time. And the highest priority one must go on the bus, which is 103. So that gets sent first. Then the next priority, which is 111, that gets sent second. Then 122, and so forth, right? So if you look at a log of the messages being sent and a timestamp log which says when each message is sent, you'll see something like this, where this message goes first, then this message goes first, it goes next, and etc. And that's the way it should work, right? As we will see, this is the ideal case. This is what we want, but there can be priority inversions that can happen, and we'll see an example of how that can happen. But typically, priority inversions occur because of practical implementation details, like the fact that buffers can only be finite sized. And so what happens if you drop messages or things like that? Yeah.
If you have 2 messages from 2 different places?
I don't know if you should look at the standard to see what happens. But I think my sense is that every message gets a distinct priority. Okay? And at least that's the way it should be implemented, right? So you can think of it as every task might be, the messages generated by every task could be allocated a separate space of priority values, and it could use that. Okay. So the goal is to compute this thing called the worst case response time. And so the main theorem that we're going to use is for the preemptive priority scheme that we're using, which is, higher priority message will preempt the lower priority message. The worst case response time of an object, a message, occurs when it is released together with all higher priority objects and they are released with their highest rate. Okay, so what this says is that if I want to determine the worst case response time of a given message, the scenario under which that happens is when that message is released together with all the higher priority messages from all the ECUs, and those higher priority messages are released with the highest possible rate that they can be released with. Okay, so that's intuitively it makes sense, right? The worst case response time happens when there's the most contention for the bus from higher priority messages. So so let's say we want to come up with an analytical formula for worst case response time, and so let's just look at what happens on the timeline. So message MI is in the queue. It needs to be sent. Let's say it's reached the head of the queue. Now let's assume that the rates of the other messages are indicated by these black and red arrows. Okay, so that's when the other messages are scheduled to be sent on the bus periodically. I sub I is the interference time. So MI is ready to be sent right here, but it's not sent until this time point. Okay, and the reason is because other higher priority messages keep preempting it. So the time in which MI sits in the queue is the interference time. So it's the time when it can't be sent, right? And at some point, MI becomes the maximum priority message, and then it is put on the bus. And there's a certain transmission time, which is CI here. And so the total response time to send message MI is the sum of the interference time plus the transmission time. Okay, there's one more component that's missing, but that's the essential idea, right? The time message it takes to be sent is the time it sits in the buffer plus the time it spends getting transmitted. Okay, so the one additional component is called blocking time. So really the total worst case response time is blocking time plus interference time plus transmission time. Blocking time is because of, it's sort of like an inertial delay, right? So blocking time is that there could be a message that's currently being transmitted, which is lower priority, but it's being transmitted right now. So the bus is not idle, right? And so if message, hex 261 comes in, then even though it has higher priority, the bus is not idle, so it has to wait, right? That's blocking time. And then after the bus becomes idle, it has to wait for all the other higher priority messages. That's interference time. And then you have transmission time. So the time spent in the queue is the sum of the blocking time plus the interference time. So the queue time for message I is bi plus I sub I. And the response time is the queue time plus the transmission time. Okay? So we can write a bunch of equations to figure out how these quantities depend on each other. So we can break up the interference time first of all. So the interference time of message I can be broken up into the interference time due to every other message j, where j is a higher priority message than I. Okay, so HP of I is the set of all higher priority messages, and the total interference of message I is the sum of the interference times for I due to every other higher priority message j. And then we can further decompose this. So the interference time of I due to j is going to be a function of how long it takes to transmit j, which is multiplied by a certain fraction. So Tj is the period at which you send message message j. So you send it every so often. And so Qi divided by Tj is the fraction of the queue time which is due to message j. And then the fraction of the time times the actual time it takes to transmit message j is the interference time. Okay, so so now we can plug this into this formula, and we'll get that qi, the q time, is equal to blocking time plus the sum of this term, right? So typically we know the period, so tj is a constant. We know exactly, different messages are sent at different rates. And we know typically transmission times, because transmission time is what happens if the message is put on the bus, and it has control of the bus, so it gets sent. So you have a certain fixed bit rate, and from the bit rate you can compute the value of Cj. And Bi, you can estimate how long it would take to wait, come up with some bound on that. So now what you really want to solve for is Qi, the time that a message spends in the queue. And now you have an equation where the unknown quantity appears on both sides. And because of the ceiling, it's harder to solve it in closed form. So the way we solve it is using an iterative technique. Just basically a fixed point algorithm. Let's, for example, you plug in 0 here, and you solve for the value of Qi. Then you plug in that value and repeat the process till you converge. Okay? So, that's a classic approach to do worst case response time. I have a bunch of papers at the end of this presentation, and this is the reference to the corresponding paper which talks about this analysis. But this is only under ideal conditions. So in a real implementation of a CAN bus, there's a whole bunch of practical issues. One of these issues we look at is the availability of buffer spaces, so that they are called TX objects, on the CAN adapter. Okay? And then there's also this issue of, in this case, we didn't really talk about the time it takes to copy a message through the different layers on the ECU, from the application software into the adapter buffer, for example. And that takes time as well, and here we've abstracted that away. So when you actually have to do analysis for timing analysis for a CAN bus, you have to consider all these cases that show up. So let's talk about one of these. Oh, so actually, I wanted to show you some real examples. So if you just focus on this one, which is the availability of buffer space, you'll find that for different boards, the amount of buffer space available varies a great deal, right? So different implementations of CAN can vary greatly in the amount of buffer space they provide, and this affects the worst case response time, right? So if you're an engineer who's using CAN, you have to think about, okay, for my implementation, let's say I have this Infineon microcontroller with the CAN adapter. How many buffer spaces do I have? Okay, it says in the spec sheet there's 32 spaces, right? And depending on that, you'd have to compute the corresponding response time. Okay, so let's assume a rather pathological case where the adapter only has a single buffer space. Okay, so here you have the same scenario we had earlier, 3 ECUs with a bunch of messages, and each of these are ordered in priority. But let's say that 261 arrived first, so it's sitting in the buffer. And then 103 arrives in the same ECU. Now clearly 103 has higher priority than 261, right? More leading zeros. So it's going to preempt that message. Okay? So meanwhile, this ECU can put 122 on the bus. So even if let's say 103 and 122 arrive at the same time, okay? So 103 arrived in ECU 1, 122 arrived in ECU 2, but 103 is preempting this message. While it's doing that, 122 gets transmitted, right? So what happened is logically these two messages, 103 and 122, arrived at the same time. But we would have expected, of course, that because they arrived at the same time, 103 gets to go first. But that didn't happen because there was some finite amount of time required for message 10T to preempt this message and then get copied into the buffer here. And by the time all that happened, 122 got transmitted on the bus. Okay? So you can have priority inversions. If you had an ideal situation where you had infinite buffer space, this wouldn't have happened because when both of these arrived, they would have arrived at the same time. And if you had no preemption delay, then 103 would have been put on the bus at the same time as 122. This would have backed off, and 103 would have been transmitted, right? Because you had a finite buffer space and finite preemption time, you had an inversion. Okay. So, and then there's the priority inversion even for message 261, okay, which is if 261 got preempted and 341 has lower priority than 261, but because 261 got preempted and because of its delay, 341 got transmitted first. Okay. All right, so this is not just a theoretical thing. So this is actual data from an automotive company, and this is a log. So in the log, what you're seeing is the, I think this is the time at which messages was sent. This field is the priority field. So this is the priority field. And so the order in which they arrived is here. So, or actually the priority order is here. So 110 has higher priority than 124, has higher priority than 308, etc. But what you find is that this message 170 got transmitted before 124, right? So a low priority message can go before a higher priority message. Okay, so that's all I talk about CAN. So we went over the arbitration scheme, which is this priority-based arbitration, and we talked about a very basic way of computing worst-case response time, which doesn't really work in practice because you have to handle all of these cases. So there's a sort of a vast literature in different worst-case execution time and not execution time, response time analysis algorithms that are used for CAN. But CAN is increasingly unable to handle the bandwidth requirements for modern cars, and so people are looking at a new protocol which has a higher bit rate called FlexRay, and FlexRay has a few interesting features which I'll just point out. So the first thing is they have a reasonable approach to doing clock synchronization, right? And one of the other things is that in CAN, one of the problems with CAN, one of the reasons the bit rate is low, the effective bit rate is low is not just because of the physical bit rate, but also the overhead of the protocol. So as we saw, in order for you to arbitrate between two messages, you have to send all these priority bits, right? That's an overhead for every message. In fact, it turns out that for every message transmission, 40% of the bits, over 40% are just overhead bits. So in FlexRay, they've introduced a few ideas which try to get rid of the overhead. One of these ideas is to do a form of time division multiplexing, where you divide up the overall communication cycle into slots. And there are two kinds of slots. So one is called the static segment. We have static slots and then the dynamic segment. The static segment is basically a bunch of reserved slots. So each ECU has a reserved slot where it alone can transmit on the bus, right? So if all the clocks are synchronized, then it helps, because then every ECU knows when the communication cycle starts and when its slot is going to be, right? And so let's say in the first static slot, ECU1 knows that nobody else is going to transmit because that slot belongs to it. And therefore, there's no overhead involved. ECU1 can just transmit, right? So I think that's one of the differentiators with CAN, where you have this static segment where you can guarantee, you can have tighter guarantees on message transmission time. But for flexibility, you'd also have a dynamic segment, right? So because if you have a static segment, then each time you'd have this communication cycle, not all ECUs will want to communicate every cycle, right? It will only want to communicate when there's a new message to be transmitted. So there can be wasted slots here. So to make up for that, they have this thing called a dynamic segment where you can have some contention and you can have variable size slots and so forth. Okay, so there's a lot of stuff about FlexRay, which I won't have time to talk about, but there's a whole bunch of papers that you can look at, plus you can just Google FlexRay and you'll find a lot of information on it. Okay? Yeah? Yeah, go ahead. It's designed at design time. The slots are assigned, right? So that's what static means. The size of the communication cycle is fixed, and then at the start of the communication cycle, all the clocks are synchronized. So everybody knows the start of the communication cycle, and every static slot has fixed size, right? And so you basically wait for that amount of time, and then you know when it's your slot.
So how do you know that this is like my slot? Is that something like
It's based on time. So you just measure, using the local clock, the ECU just measures the time to its slot.
Oh, but I mean, like, how do they know, like if this is my slot versus like something else? Like, they decide is there priority?
It's sort of hard-coded in, right? Yeah. That's what static means. It's basically fixed for the duration of the operation of the system. Okay. So one of the things we talked about in FlexRay, which is becoming really important for embedded systems, is clock synchronization. And this is a topic that's been studied a lot. So just commodity computers on the internet, they're synchronized using NTP. Right? Many of you might have heard about it or read about it. The synchronization fidelity, though, is not that great. So it's of the order of a few milliseconds. But for a lot of embedded applications, you need much lower, much smaller synchronization skew, right? So of the order of nanoseconds. And that's what IEEE 1588 was geared towards. So how can you just use Ethernet, which is a protocol that we already use widely, but adapt it to real-time embedded applications? So I had a guest lecturer, John Eitzen, who was involved in creating the IEEE 1588 standard. And so he gave a guest lecture at 149 2 years ago. And so I have the complete set of his slides on the website. So you can go and look at that later if you're interested. I'm going to just talk about a few selected ideas here. So the purpose of IEEE 1588 is basically to synchronize clocks in a networked embedded system. Now, it doesn't specify anything about how you should use those clocks. So you can build your own application and figure out how to use synchronized clocks. This is only talking about how to get all the clocks of the different nodes, basically recording time with very, very small skew, nanosecond scale skew. It's actually already widely used. So it's being used quite a bit in power generation systems. Industrial automation, I'll give you an example of that. It's used in cell phone network backends. So in base stations, so in different cell networks, base stations, they have to be time synchronized. And that's where it's used. And then it's used in a whole bunch of other applications. So I don't know if we talked about this earlier in the course, but this example of a modern printing press where you have basically microcontroller units in each of these units that dump a particular kind of ink, and you have Ethernet cables connecting all of them. These are running 1588 because all of these need to be synchronized in time because the paper zooms through this printing press at really high speed, right, 60 miles per hour. And so any skew or any mismatch can lead to a huge mess and a large loss for this printing press. Another case where 1588 is used is in instrumentation. So in aircraft, like Boeing's aircraft, they have to often do a whole bunch of testing, right? And the way they can do these testing and get various diagnostics from different parts of their system is they basically connect a unit and collect data, and the data has to be time-stamped. So they need to know what are the events that happened at different nodes on the plane at a certain time point, right? And for that, they need to get accurate timestamps of the different events, and they get that through 1588. I've already talked about cellular backhaul. That's another application. Okay, so let's talk about one aspect of the clock synchronization algorithm. There's a whole bunch of things involved, but I'll just talk about one of the parts of the protocol. So one of the key ideas in 1588 is let's say you have 100 nodes, right? You want to organize these nodes into some sort of master-slave pair. So one node serves as master and the other serves as slave. And the slave node will synchronize its clock to the master. Okay? So that's the general idea of the protocol. So you have a network. The network organizes into maybe a hierarchy of master-slave pairs. And then each slave synchronizes to the master. And then there's one global master. And so everybody synchronizes to that. Okay? Now, how do you figure out who the master node is? Right? That's a key problem. That's actually a very classic problem in computer science called the leader election problem. And protocols to solve this are the leader election protocols. So the idea is you have a bunch of nodes on a network, and they're running the same code, essentially. And one of them has to be elected to be the leader. So what's the protocol you follow to do that? So we won't go into this again today, but the idea is you run a leader election protocol to organize the network into master-slave pairs, right? And the overall leader is the global master of this network. So I think that's what he calls the grandmaster. So the grandmaster synchronizes to his slave. This might be the master for somebody else, etc. Okay, so now let's look at what happens once you've figured out this, once you've elected the leaders and you have these master-slave node pairs, then let's look at what happens, what are the sequence of messages that go between a master and a slave. Okay, so this is the timeline for the master node. This is the timeline for the slave node. Okay, so time basically goes from top to bottom, increases from top to bottom. One important thing to note is that these timelines are potentially different, right? Because the clocks at the master and the slave are not yet synchronized, right? And there could be even a slight skew in the rates, okay? So what happens is first the master sends a message. So at time t1, according to the master's clock, the master thinks it's time t1. So according to time t1, at time t1, the master sends a sync message to the slave. The slave receives this at time t2 on the slave's clock. Okay, so the transmission delay is effectively t2 minus t1, right? With accounting for the skew, right? So this t master to slave TMS is going to be the sum of the actual propagation delay plus any skew. Then the master sends a follow-up message, and the follow-up message contains the value of T1. So the master records the value of T1, and it sends it in a second message. Okay, that's called the follow-up message. So when the slave receives the follow-up message, the slave knows T1, and it also knows T2. Okay, so the next step is it goes the other way. So the slave at time t3 on the slave's clock, it sends a message called delay request, and the master receives that at time t4. The master then sends a response which contains the value of t4. So when this message is received, the slave knows not only t1 and t2, but also t3 and t4. Okay, remember, T2 and T3 correspond to values on the slave's timeline, and T1 and T4 correspond to values on the master's timeline. Okay, and this time the skew plus propagation delay from slave to master is TSM. Okay, so TMS, time from master to slave, TSM is time from slave to master. So now we can write a bunch of equations that will allow us to solve for the value of the offset and the value of the propagation delay. And the assumption we'll make is that the link is symmetric. So the time it takes for a message to go from master to slave is the same as the time it takes from slave to master. You can get rid of that assumption and then do a more elaborate analysis. But for simplicity, we'll consider the symmetric case first. So what's the definition of offset? Offset is going to be the difference between the slave clock and the master clock. So more specifically, the value at any instant, the value at the slave clock minus the value at the master clock. Right? So when I say at any instant, it's as if you know what the global time is, and at that time instant, let's say you have say God is looking down at the network and has a clock and records the times at every node, right? And records the time at the slave clock and the time at the master clock, and the difference between that two, the two of those is the offset. Okay. So now we can write down TMS and TSM in terms of the offset. So T to master to slave is going to be the offset between this. So T2 minus T1 will include the offset plus the propagation delay. Right? Now, if you go the other way from slave to master, then you have minus offset, right? So when you look at the delay going from here to here, you're taking the receive time. Again, you're looking at the actual time. So the actual receive time minus the actual send time with respect to this God's clock, right, is going to be the skew plus the propagation delay. But the skew is going the other way. Okay. So it's going master minus slave, whereas I've defined offset as slave minus master. So that's why we have a negative sign here. So you have minus offset plus propagation delay. All right. So now we have these two equations. TMS is equal to offset plus delay. TSM is equal to minus offset plus delay. And assuming the link is symmetric, these two quantities are the same. Right. So MS delay is equal to the SM delay. And so you can then solve for offset by simply subtracting these two, right? So you don't know the delay. This is a variable, but we assume these two variables are the same. So when we subtract the two equations, that disappears, and we can solve for offset as TMS minus TSM divided by 2. Okay. And then you can solve for the propagation delay by adding the two equations together, right? So that's how you'd solve for the offset and propagation delays, assuming the link is symmetric. All right, so that's all I'm going to say about 1588. There's a lot more information at this website, including a quite nice set of slides that goes through this topic in tutorial form. And that's it for today's lecture. Are there any questions? No? All right. So remember, Tuesday is the midterm, and we'll send out an email talking about exactly what part of the material covered before the first midterm will be on the syllabus. Yeah. Sorry? Yeah. So the end of the syllabus will be till the end of chapter 15. Right? So what we covered today and the material on fault tolerance is not in the midterm.